You're listening to MedX, the Medical Extrusion Podcast. Presented by U.S. Extruders. Extrude with confidence. Custom extrusion equipment designed for you and your application.
Welcome back to the MedX Podcast. I'm Steve Maxson. Today we're talking about high grip surfaces, and our guest is Ralph Hulseman, President and CTO of Hoowaki. Hoowaki solves challenging grip or slip problems by adding microsurfaces to components and medical devices. Ralph, thanks for joining us today.
Thanks, Steve. I'm very glad to be here.
Great. Ralph, before we get started, please tell our listeners how you got involved in the business of developing microsurfaces for medical device components.
Yeah, Steve, it's kind of crazy because we've pretty much invented this field. So my background, I'm a rubber guy. I spent 25 years at Michelin, all in R&D. And as you might imagine, Michelin knows a lot about friction and wear and materials and so on. And even as early as the 1980s, Michelin knew that basically tire traction occurs at features in the micron range. So a micron is a thousandth of a millimeter. And so most of your friction occurs between a few microns and a few hundred microns. And at that size, it's too small, or it was at the time, too small to physically make samples for things like testing samples. So a dream in Michelin always been to have ideal friction surfaces that you could make friction laws and well-characterized things. And so we spent a number of years looking for that. And in 2006, I ran into a professor at Georgia Tech, Bill King, and he knew how to make those structures. And so we commissioned that, and away we went. And eventually that led to Bill and I and a third gentleman to found Hoowaki. And I left Michelin, and away we went.
That's a great story. Thanks for sharing. Ralph, there's so much going on today with low friction materials and alternatives to PTFE due to supply chain issues. But let's start with the opposing topic from slippery surfaces and talk about adding friction or high grip against wet, soft human tissue to prevent migration of devices such as a fully covered stent. But before we do that, let's kind of lay the groundwork and tell us what the difference is between high grip or anchoring and slippery or tacky surfaces.
Yeah, so Steve, for us, it's a matter of design of the microsurfaces, and we go either way. And basically, to have real high grip, you put surfaces on a stiffer material to indent the other side and kind of dig in, not cutting, damaging, but to indent a bit and create friction. On the low friction side, we do the opposite. You put surfaces on the softer material, reduce the area of contact, try not to have any deformation, and you can reduce friction. It's kind of interesting because, as you mentioned, on the low friction side, we have lots of competition, PTFE, lubricants, and so on. On the real high grip, we really don't have direct competition. We compete against things like sutures, but in many places you can't stitch something down. A little bit adhesives, but again, adhesives are not really used so much in the body, or they're problematic. So we provide a unique solution there for things like anti-migration to keep stents from moving out of place.
Okay. So the micro grip surfaces can be formed on thermoplastic materials like polyurethane, polyethylene, I think Dacron. Can it also be added to thermoset silicone and expandable PTFE?
Yeah, so Steve, we can put these micro features. First, we machine them in metal, or we have other routes, EDM and so on, but we get them in metal. Usually that's for tooling because of price, but we do make a few metal tools, a few metal end objects. But then the metal tooling can form any polymer that will hold its shape. So thermosets like silicones, olefinic rubbers, Dynic rubbers, and so on, epoxies and so on, and any thermoplastic. Where we have difficulty is materials with very high cold flow, like a very low density polyethylene, um, or materials that don't hold their shape when you demold. So, for example, something with a lot of graphite carbon in it that has a plate-like structure, when you demold it, they will just simply fall apart. So we can put features in PTFE before the sintering, and the features stay there. In expanded PTFE or foams, we can't do it because you crush out the porous structure.
Mm.
So, we can take a piece of expanded PTFE and make beautiful micro features in it, but then it's no longer behaves like an expanded PTFE and you lose those properties.
Okay, interesting. When I look at a microscopic image of the micro grip features that protrude from the substrate, I notice that there's two levels that protrude. There's a base pillar, and then the micro features are formed on the top surface of that base pillar. Talk a little bit about why there's a hierarchy of pillars there instead of just adding the micro surfaces directly to the substrate.
Yeah, Steve, that was the multi-level patterns were one of our steps through to try and achieve this high indentation pressure. So I talked about, to get high grip, you need to indent the opposing surface. You need to concentrate pressure on the tips of the micropillars. And so the trick is, how do you make them small to concentrate the pressure without having them buckle and fall over? And particularly on something, an irregular surface like tissue, you need to have some height of the pillars to penetrate into the tissue. And so if you make a single tall pillar that's just perfectly straight and vertical, they tend to tip over.
Mm-hmm.
And when we started, we were limited to silicon lithography. So we take silicon wafers, like the one I'm showing here. It actually has a micro pattern. It looks just shiny and blank in the photograph. And we make the structures. Well, when you're etching silicon, you're limited to straight vertical walls. You can't do a draft angle, or not easily. So one way to get taller features with smaller area on the end to concentrate pressure, was to stack them up. Mm-hmm. So you have one level at about a 1-to-1 aspect ratio, height to width. And then you put on a second level, smaller, with more smaller ones, 1-to-1. And that way you can get some overall height to penetrate in the tissue and still concentrate pressure. Now we've moved to other technologies as the technology evolved, and we micro machine. So I'm holding up some bits to the camera, and if it'll focus small enough, the one all the way to my left is a 50 micron bit. So it is about half the width of a human hair. And the advantage of micro machining at this scale is now we can do things like draft angles. So we can make angled features where you have a single cone-like feature to concentrate the pressure, to still have strength against bending and so on. And we've kind of moved beyond the multi-level patterns. And kind of the newest evolution of our design is what we call clusters. And this is a little bit like putting a tire tread. If I go back to my ancient roots, they never let me design tire treads. But anyway, I'm inspired by their great work. And so here we can have groups of pillars where you can concentrate the pressure and have room for the fluid to flow around them. And that gives us even another step up in wet grip. So, when we started, it was kind of all simple fields of uniform pillars. And then as we, step into the technology, our engineers get more and more creative how to get, higher grip without trauma. And really big push now is to figure out every tissue in the body, whether it's bone and tendon or a soft serosa covering an organ or so on, and figure out how can we get the maximum grip without trauma. Or some customers, it means just the right level of grip. So for example, a balloon, say for example, in your intestine, if there's a problem goes wrong, like with a robot or something, and that balloon is jerked,
Mhm.
you want it to slide rather than tear the intestine. And so in a lot of our applications, it's that way. How do we get the maximum performance out of the device while ensuring that there's just no risk of trauma if things go wrong or just ordinary behavior?
Yeah, interesting. There's a fluid dynamics component to it as well, as you mentioned.
Oh yeah, we've done a lot of work there, and viscosity of the fluids is important. And so you can imagine, how clutches work or automatic transmissions, where the viscosity of the fluid is important.
Hmm.
Well, thin films, you can use that same kind of viscous drag effect to create significant adhesion, significant grip, if you will. And then also, as films get very thin, the surface tension can pull that film down on the tissue. So what we call the suck down.
Hmm.
So you don't really need a normal force holding it in place. The surface tension of the fluid will in fact hold it in place itself. And that's important in applications like hernia mesh, barrier films,
Hmm.
and things where during surgery you want it very easy for the surgeon to position it, hold in place, smooth out, avoid any wrinkles. Maybe they need to pick it up and adjust it. And then when it's just right, they can do a final stitching if they need stitching.
Right.
And particularly important in robotic surgery, where, with an open surgery, our technology is not that useful for
Hmm.
helping during the surgery itself, because the surgeon can, they got 2 hands and 5-10 fingers and they can fiddle with it. And laparoscopic, it becomes more important. And with robotic, it becomes really, really important to have just the right grip and friction.
Wow, very interesting. You mentioned high grip without trauma. So let's talk a little bit about some applications. And I know that one area that you're working on is adding high grip anti-migration technology to fully covered esophageal stents. An esophageal stent is used to treat strictures within the esophageal lumen to prevent closure. And as I was preparing for this podcast, I was reading an abstract from a medical journal, and it talked about the migration of fully covered self-expandable stents within the GI tract. And I was surprised to read that, 1/3 of the cases, there's stent migration. And that's kind of shocking to me. And I know there's conventional methods to kind of anchor the stent, the fully covered stent within the esophageal wall, such as endoscopic suturing and the placement of clips. And I know some of the designs of the fully covered stents have sort of like a dog bone shape or flared ends that include barbs and hooks that could potentially lead to trauma. Walk us through the microsurface pattern on the outer surface of a fully self-expandable, fully covered stent to prevent migration against a sort of a wet esophageal wall.
Yeah, thanks, Steve. That's a good question. So for the viewers that will see this, I will hold one up to the camera and try and get it close. And as I kind of zoom in, you might barely see a little roughness there.
Mm-hmm.
In fact, the microsurface is invisible. It doesn't change the behavior of the stent in terms of stiffness or elongation or so on. And but it does add a great deal of grip. So on the order of 5 to 8 times more pull force. And as you mentioned, Steve, it's pretty shocking, that rate of migration. And the industry has been trying several things. Some areas of placement, they can use sutures or clips. But in a lot of areas of the esophagus, the peristaltic motion of swallowing is so strong that it will rip out sutures or hooks or so on. And they, when they just started in this area, they tried to use uncovered stents. They would keep the structure open, but you'd get so much ingrowth that at the end of even a couple of weeks of healing, it was really traumatic to literally rip these things out of the tissue. So they've gone to the covered stents, keep the stricture open, allow it to heal, avoid that traumatic tearing after healing, but they have a high migration rate. And that's where we come in. And in full-size pig studies, everybody else's stent goes out one end or the other of the pig within 24 hours. Ours stay in place for 30 days, the length of the test. And at the end of the test, they pull the stent out. You see bright pink healthy tissue, see an impression of the micropattern for a few hours, and then that disappears. And seems to be a wonderful solution. It's being used in a variety of applications there. One I really like is emphysema treatment devices, these little endobronchial stents, where the first generation are kind of covered with hooks. They implant it in the lung to stop the spread of the emphysema. But then as the disease eventually spreads, they have to apply more and more of these. And with ours, it holds itself in place. The surgeon can go in later and adjust it, can move it as disease spreads. And so it's simpler surgeries, less traumatic, lower cost, and so on. And those are now in human trials, and we look forward to seeing them appear on the market. Fortunately, a lot less people in the U.S. are smoking. Emphysema is kind of declining as a problem here, but other parts of the world, it's still a huge issue.
I know that it takes a long time for some of these devices to go from early stage prototyping, V&V, to full scale commercialization. Have any of these developments that you've been working on, in particular the GI tract, have they gone into commercialization yet?
None of them yet. So there's a barrier film application that's FDA approved and on the market. Hernia mesh products are moving along, esophageal stents moving along. COVID was a big hit for us. We have some projects today that are the same place they were at in February 2020.
Yeah.
And, it hit our customers hard. And you mentioned supply chain at the start of the discussion. And so, when they can't get silicone to make their production devices, they don't want to do too much on R&D and so on. So, no, things are moving through the pipeline, but not yet fully on the market for the high grip implantables.
Yeah. Okay. Yeah, I look forward to following that. It's very interesting technology. I had Dan Kasperzik on the podcast recently. Dan is the founder and CEO of POBA Medical, as you're aware, and you kind of have a co-partnership, a co-development of an application where you're adding high traction to the surface of balloons. People know Dan and POBA as one of the leading developers of balloon technologies. And so you're working on a project to improve grip between the GI tract or the vasculature. And in particular, there's an issue when a balloon is inflated within a target site. It has a tendency in some cases to kind of move out of position. It's referred to as watermelon seating. Yeah. Can you provide an update on any the status of that co-development with POBA?
Yeah, we're working very hard with them. Just got a new batch of Parison tubing last night from them for our next step. And for dip balloons, you can put the features on the dip mandrel and it works pretty well. For blown balloons, it's been a much tougher challenge. And first, we thought too, you could put the features on the mold for the balloon. And it doesn't work at all. It turns out that when you blow a balloon, by the time the expanding balloon hits that cavity wall, it is too cold to form micro features. And if you try and heat it up to where it'll form nice nitro features, then the balloon will burst. It can't quite get there. So we've had to step back and think of another route, which is to put the pattern on the tubing that forms a balloon before it's blown. It's called the parison. And the trick there is you have to have quite a different pattern on the tube so that when it expands in blowing, and they expand 500, 700%. So you need to have it expand into the grippy zone. And so what that means for us is it's a different, if you will, a dense pack pattern on the tube that then expands very nicely into something that grips. And then balloons see lots of different anatomy. And if you do something like a feature too tall on too soft of a base layer with, too little inflation, it can tip over.
Yeah.
And so lots of kind of tricky design issues, and we're working with, and fortunately, Dan and his team have been very patient. I think they're kind of excited. They see something interesting at the end, but it's been both a manufacturing challenge, a design challenge, and then a challenge to figure out how balloon works against different anatomy or against things like expanded PTFE covered stents or steel stents or so on. So journey still underway. We'd love to have projects come along, as long as our customers understand we're still plugging away developing, and maybe they'll be the lucky one that now it's just right the first time.
Yeah, that's interesting. Yeah, it's a lot of iterations and development to get to where you need to be there. So look forward to following that project that you're working on with Dan and the team at Proba. Let's wrap things up and talk a little bit about extrusion. This is the MedX podcast, and a lot of folks are interested in extrusion. And recently, I had Jonathan Georgatis from Spectrum Plastics Group on the podcast. He was talking about the work that he and the team at Spectrum Plastics are doing to extrude and evaluate alternative materials to PTFE, again, due to this supply chain issue. And one of the things that Jonathan talked about was adding or modifying the surface of, for instance, FEP tubing to kind of create peaks and valleys on the outside surface of the tubing or inside surface to reduce the contact and potentially reduce the coefficient of friction. Talk to us a little bit about some of the work that you can do with tooling and add micro surfaces to the ID or OD of medical tubing.
Yeah, so we've, again, for those that are watching, I'll try and hold up a couple samples. And here on the left side of to me, is one that looks a little frostier.
Yep.
On the right side, one that's more clear. And so the frostier one, in fact, has about 40% more slip than the transparent one. And in this case, in a demo tube, it in fact has the micro pattern on the inside and the outside. And so on the inside, we put the micro pattern on the mandrel. And again, I'll hold up for those watching. You see some small lines on the end here.
Yep.
And on the outside of the tube, it's put on the inside of the outer die. And of course, during extrusion, the polymer relaxes, you have drawdown, it changes shape. So part of our patented technology is how to make the features in the die so that they end up with the right features on the extruded product. And by the right features, what you want is very uniform pressure where they touch the wall, so meaning flat top features. And then you want as little contact as you can without them bending, buckling, and so on. So you want to spread them out. So we want little square-shaped ridges on the extrusion. Now, if you just put a slot in a die and extrude, you get kind of a rounded lump. And the difference between that rounded lump and a nice square feature is as much as doubling the performance.
Okay.
And so it's kind of a nice technology in that on a hard plastic, you get a 40-50% reduction in friction. So something like a nylon will come down to where PTFE is. In fact, it works on PTFE and you can reduce further. Now, it's not the performance of a lubricant, like one of the hydrogel lubricants, but it's far cheaper and far easier to qualify. There's no particulate risk, no contaminants, and so on. In rubbery materials like silicones, it's a bigger difference, up to 80% or so. And in particular, it stops the kind of stick slip. And I don't know if that's the most volume of tubing that's in use today for this is silicones, where it stops like, if you want to just have a cable cover to drag around the surgical suite, it won't hang up anymore.
Okay.
Or, and so on. Then an interesting use of the tubing is to make it easier to assemble the layup catheters. So when you do the reflow in a layup catheter, you melt out the microfeatures. So we've never figured out how to replace the PTFE liner inside a reflow catheter. Maybe we'll get there someday.
Yeah.
But just easing assembly is kind of a nice application.
Okay, so that's interesting. So, these applications where folks are trying to find alternatives to PTFE, that is for an inner liner of a composite catheter shaft. And what you're saying is if you use an alternative material, for instance, that has a micro feature on the ID so that it slides over a guide wire, right? That during reflow or the lamination process, you will lose those micro features.
That's right. They melt out. So it's used in some simple catheter constructions where it's a simple tube or maybe a tube with a braid over it with another tube that's just all extruded. So works well in those applications. It turns out we can, in fact, machine the patterns onto the mandrels for the reflow catheters. And the pattern forms nicely. We've not figured out a technology to get the catheter off of that mandrel reliably, particularly when they're tiny diameter and long. So if it's kind of a short, stubby catheter, maybe something a foot or two long and 6 millimeters or more in diameter, then we have a solution. But really the high value, long vascular catheters, we just need somebody to come up with a really good lubricant technology for us to help with those catheters mandrels apart.
Yeah. Okay. Very interesting. That's good information. Hey, Ralph, this has been a fascinating conversation. Thank you so much for joining.
Thanks, Steve. Appreciate your having me on and love the podcast.
Great. Thank you so much.
Bye-bye.
Thank you for listening to MedX, the Medical Extrusion Podcast, presented by US Extruders. Please subscribe to make sure you're getting the latest episodes. All links are available in the show notes.